Welcome to our tutorial of ProfLearn YouTube channel. In this particular video, we are going to have a discussion on the topic temperature and thermodynamics. This is paper 4 of Cambridge 97025, 9702. So we're going to see structured questions on how you're supposed to approach different questions when you are given a paper of A-level physics. If you are new to ProfLearn YouTube channel, consider subscribing so that anytime I upload any video in this channel, you'll be notified. And if you have not joined our Patreon page, join so that you can be able to access this PDF that you can see I'm having at this given point. Without much ado, let's now dive in so that we can be able to get started. In this topic, temperature and thermodynamics, you need to understand a few concepts. You need to understand how to define specific capacity. And you can see here the examiner was asking, how do we define specific capacity? So something that we need to realize here is that specific capacity is the amount of thermal energy required to change a temperature of 1 kg of a substance by 1 degree Celsius. So that's exactly what you are supposed to mention at that given point. Then in this year of 2025, another question that was asked is explain why the substance explain why for a substance the specific latent heat of vaporization is greater than specific heat capacity. Remember, specific latent heat of vaporization involves changing a liquid to gas, meaning that for gases, we know that the intermolecular spaces are bigger compared to liquids. So if we are talking of states of matter, you can see here in the states of matter, solids, particles are closely packed. Liquids, there is quite some space for there are large intermolecular spaces, but for gas you need to separate the liquids, the molecules a bit much further, and that means that you require a lot of energy to do that. So which means whenever you are supposed to respond to this particular question, you are to talk of the intermolecular spacing and also separating the molecules, and also there's involvement of a larger volume when you are converting a liquid to gas. So we could say specific latent heat of vaporization is greater than that of fusion because vaporization involves much greater increase in separation of molecules and a larger change in volume takes place in that case. So that is basically what you are to focus in that particular area. And once you've told the examiner that, the examiner will just be giving you the 3 marks, and then we need to proceed to the next part. We are told that ice cube, we are told here that ice cube of mass 37 grams at 0 degrees Celsius. So you need to understand that quantity of heat to melt a substance is mass times the latent heat of fusion. So if we want to calculate the latent heat of fusion, we are going to say is 0.037 times latent heat of what? Fusion. Okay? And which we are going to identify that as latent heat of fusion here, so that we don't confuse. Amount of heat required to melt a substance is the mass times the latent heat of fusion. Then heat used to raise the melted ice, because when the ice melts it's going to become water, and that water will be at 0 degrees Celsius. So you need some heat to change that from 0 degrees Celsius. We change it to 10.3 degrees Celsius. So the amount of heat required to do that is MC change specific capacity times change in temperature, and the change in temperature is going to be 10.3. So we shall say 37 times 4.18 times 10.3, and this is the value that we are supposed to get there. So the amount of heat required in that case is 1593 joules. But let me mention also, if in a scenario or in the event they are going to give you a question whereby they have given you specific capacity in kilogram joules per kg per degree Celsius, you have to ensure that the mass is in kgs. So don't forget that. Now, the heat that is lost from the hot water is the one that is going to be absorbed by the ice to melt it, and then also to raise the temperature to 10 degrees Celsius. So heat that is lost by water is going to change the temperature from 26.4 all the way to 10.3. So the temperature change will be change in temperature for the hot water is going to be 26.4 minus 10.3. So if you work out, this is going to be 16.1. Yeah, so the temperature change is going to be 16.1, the one that you can see I'm having here. Okay, so once you have gotten that, we are going to say now latent heat of fusion, the heat of fusion plus the heat that was absorbed to raise the temperature should be equal to the amount of heat that was lost by water. And then we are going to make LV the subject of the formula for you to earn those marks. So if you work it out, you're going to get 335 joules per gram. Now, the next question that is being asked here is, state what's meant by internal energy. Internal energy can be defined as the sum of random distribution of kinetic energy and potential energy of atoms or molecules of a system. Because internal energy is given by the kinetic energy of the molecules plus the potential energy of those molecules. So basically, you need to know how you define internal energy. Explain why the internal energy of an ideal gas is directly proportional to the thermodynamic temperature. Why is internal energy of a gas directly proportional? Ideal, and specifically we're talking about ideal gas. So something that we need to remember for ideal gases, there is one of the assumptions that we mentioned when we were learning this in class about ideal gases. Let me just show you. These assumptions we mentioned here. Particles are in a continuous random motion. Particles are negligible volume compared to the volume of the gas. Random collide perfectly inelastic. Molecules exert no force on each other. So in that way, because that force exertion is the one that is going to bring the effect of potential energy. So for that case, we're going to say for ideal gases, potential energy is 0. So what determines the internal energy of an ideal gas is explicitly the kinetic energy. And kinetic energy is directly proportional to temperature. Because if you increase temperature, thermodynamic temperature, you're increasing the kinetic energy of the gas. And having that the internal energy is determined only by the kinetic energy of the gas, ideal gas, then it means the internal energy is directly proportional. So we're going to say internal energy of a gas is equal to potential energy plus kinetic energy. Potential energy for ideal gases is what? Is 0. Yeah, and internal energy depends only on kinetic energy. So, but kinetic energy of a molecule is proportional to the thermodynamic temperature. Yeah. Because I believe you remember the aspect we say that kinetic energy of a gas is equals to kT. Do you remember this? Yeah, do you remember this? If you remember, then you are in the safe side. So from here we can see that kinetic energy is directly proportional. You think I'm joking? We did that, guys. So we did that, huh? We did that. Let me just, yeah, something like that. Yeah, we did this stuff here. Half k, yeah, this is a third kt, which means a third times the Boltzmann constant, yeah, times the temperature. So this is the relationship, and then for that reason you're gonna realize that that is going to be that. And a sample, there is another question here. We are told that a sample of ideal gas at thermodynamic temperature T has internal energy U. Yeah, so we have thermodynamic temperature T has internal energy U. The gas is compressed to so that its temperature increases to 3T. Temperature increases to 3T. Yeah, it's during this compression, work done on the gas is W. During this, work done on the gas is W. The gas is then cooled down at constant volume. So if you are told constant volume, it means this change in volume is going to be equals to 0. So if you are told constant volume, it means change in volume is equals to 0. And when there is a change in volume, work done is 0. Because we know work done is equals to work done, we know it is pressure times volume. So if work done on a gas is pressure times volume, and then you are being told that the volume in this case, the volume is basically 0, then it means the work done in this case is going to be what? 0. Because pressure times 0 will give you 0. And thermal energy supplied to the gas. Thermal energy supplied. Thermal energy supplied to the gas. So we know thermal energy can be given by the first law of thermodynamics, which is going to be equals to internal energy is equals to the thermal energy supplied plus the work done. Now in this case, if the work done is equals to 0, then it means that thermal energy is equals to the internal energy. So, and internal energy in that case, yeah, is going to be equals to negative U, because if you are saying Q is equals to AU and thermodynamic temperature is basically thermodynamic temperature, we were told it was T. It was T. So thermal energy supply is equals to KT. Why are we saying that? Because we have said that change in internal energy, let me just write here, change in internal energy is equals to energy that is supplied plus the work done. And the work done in this case is going to be 0 because there is no change in volume. Which means that you are going to remain with this particular equation here that is without W. So it will be thermal energy supplied is equals to the internal energy. And the internal energy of a gas is determined by what? Internal energy of the gas is determined by the kinetic energy. So which will mean that now when we are looking at the thermal energy supplied to the gas during compressions, we are told that when it's compressed, work done on the gas is W. work done on the gas is W. Yeah. So which means that the internal energy is going to be plus 2U. If we are talking about thermal energy supplied, it will be 2U minus the work done. We also have increase in internal energy and thermal energy supplied to the gas during cooling. That is going to be increase in internal energy is going to be negative U, because it's cooling, so it means we are going to have a negative there. And then thermal energy supplied to the gas is negative U. Again, the question on definition of specific capacity is a question that has been featuring quite a number of times. We are supposed to calculate the mass of the block in this question, and here you are to say mass equals to density times volume. We were given density, and then the volume also was provided here, so meaning we are going to say 2.7 times 10 raised to power 3 times 3.6 times 10 raised to power negative 3. If you work it out, you are going to get your answer equivalent to 9.752 kilograms. Show that the volume of the block at the temperature of 500 degrees Celsius is that. So we know that for both cases, the mass is going to remain constant. And we know that mass is density times volume, because if you rearrange this equation, you'll have the equation that mass is density times what? Times volume here. So meaning we are to use this expression that for both cases, mass is to remain constant, and then we shall have density at 0 and volume at 0 is equals to density at 500 times volume at 500. So that we can be able to get the volume of the block at 500, we must have had this particular expression. Use the information to determine the magnitude of the work done. When they are telling you magnitude of the work done on the block, we are going to use the formula work done is equals to density negative density times volume. This is the conventional way of writing work done. It's pressure times change in the volume. But since they are specifically talking of magnitude, we are going to consider taking the answer to be a positive value, and we shall take the pressure was given there, and then we have a change in volume. We are going to subtract the 2, which is going to be 11.11 as the work done. Explain whether work done on the block is positive or negative. So what happened in this case? If you look at it, what happened in this case, you have to check is did the volume increase or did the volume decrease? Now, change in volume, if volume is positive, if change in volume is positive, it means that that is an increase or an expansion. And when a substance expands, it does work to the surrounding. If you have change of the volume negative, it will mean that that's contraction. The substance is contracting. So meaning that work is done on that particular object. If you are asked the work done on an object that is contracting, or the volume is shrinking, or the volume is becoming small, you need to remember there and say that work done by that object is negative, because it's not doing work. Now, in our case here, work done on the block is negative because the volume work done on the block is negative because the volume increased, but work done by the block is going to be positive. I don't know whether you are getting me. Work done by the block is positive, but work done on the block, they are asking work done on the block, is going to be negative. Yeah, so the atmosphere does negative work on that. Use the first law of thermodynamics to determine the three significant figures. So sometimes we are not going to use this law. You are not going to state all this. This one I just mentioned because I'm going to take you through this so that you can be able to understand what we're doing. So change in internal energy is equals to energy supplied minus the work done, and we had gotten the work done was 11.11. so, and also the change in internal energy, were we told change in internal energy now, so internal energy of that it was provided here, well seated here. The block increase internal energy is 4.38 mega. So mega means 1 million. So we are going to say change in internal energy is equals to heat supplied minus the work done, and the work done is here. So if we rearrange that, we are going to have our change in the heat supplied to be this value, which is 8. So what did I do here? Change in temperature is this, then we are going to use MC change in data to get the quantity of heat. Once you have the quantity of heat, of course the quantity of heat is this value that we have gotten from here, then you will say that MC change in data is equal to this, and change in data is 500 because the temperature was changing from 0 all the way to 500. And having that, if you equate this part and see the subject, you are going to get this particular value that we are having at this given point. Without further, I can suggest with a reason how doubling the pressure is likely to affect the answer. So work done is negligible and compared with the change in internal energy, so the answer above will not be affected, because you see here we are having 3.38 times 10 raised to the power 6 plus 11. This is the value that is coming from work done. So even if you double the value of pressure, the amount of work done will be so small that it's not going to affect our value here. We are given equation of state, and at this given point we are supposed to identify the meaning of symbol T. T is the thermodynamic temperature. B that we are having here is molar gas constant, mostly denoted as R. You can see now from this particular part, you can have this as the molar gas constant here. And then state the meaning of the symbol C squared. This is the mass of a molecule of a gas. M is the mass, and C squared, this is the mean square speed of the molecule. Use the equation in A and B to derive the expression in terms of that. So we have to remember that PV is equals to N dt. Then we can be able to say PV is equals to 1/3 N mean square speed Then if we equate this particular part that we have to the kinetic energy, we are going to simplify, and our kinetic energy is going to be given by that particular expression, kinetic energy of the molecule. Yeah, so in the event they are asking you to draw a graph to represent that, is going to be a graph that looks like that. Because if you have this, you will come to realize that the root mean square, by just deriving, I just took kinetic energy equation, I equated to whatever that we are having here, and you realize that if you make the root means the root mean speed subject, you are going to have cube root, a square root of 3r over m, but 3r and m, these are just constants. So meaning you are drawing the root mean speed is in directly proportional to the square root of t. Yeah, so that you are going to have a graph that looks like that. Because when we were learning about y is equals to root x, that graph looked like that. Y is root x, that graph looks like that. That's why we are saying that graph will look that way. Now, another aspect that you need to understand is the aspect of thermoequilibrium. Sometimes you'll be asked to state what do we mean by an object is at thermoequilibrium. Yeah, an object, two objects are said to be at thermoequilibrium if there is no net heat flow between those two objects. So there's no heat flow between the two substances. Yeah. Okay. Heat gained by the ice to melt it is going to be the mass of ice times the latent heat of fusion, and latent heat of fusion for ice was given here. Heat lost by waters decreases from T to theta, so temperature change will be T minus 0 minus theta times mass times specific heat capacity, and that is exactly what you got, and then you are going to paint it here for the examiner to mark. Heat gained by melted ice. Ice will melt and become a liquid. That mass of a liquid is equal to the mass of the ice that was there. So you're going to take the mass of ice, which was x, times specific capacity of water, because this ice has melted to become water, times the temperature change. Because the temperature will change from 0 to x, to theta rather, it becomes that. And then use B to answer to find the final temperature, and in that case you are going to use the concept of heat lost is equal to the heat gained, and when you just work it out there, you are going to rearrange and arrive at this given point until you understand that you can be able to move to the next part. State what's meant by the ideal gas is another aspect that you have to put into consideration. Ideal gas is a gas that obeys this particular equation that we are having here. A gas that obeys this equation is an ideal gas, and it has to obey it at all values of P, V, and T. Yeah? Where it is the thermodynamic temperature. An ideal gas of pressure this and mass density of this show that the root mean speed is approximately 500 meters per second. So something that we need to understand also at this given point is that we are going to use the formula pressure times volume is equals to a third number of molecules times the mean square speed. And then if we try to make these subjects, we are trying to make root mean speed as subject, we shall have our expression written here. And we need also to put into consideration that when you're having this equation, m over v is appearing here, and that means it's going to convert this to density when you have mass over volume. Mass over volume, because you can see we are having the mass here and we having a volume here. That one becomes what? Density. Yeah, so of molecules. Then if you are going to do the substitution there, that is 3 times the pressure divided by the density, we are going to get our answer reducing to that. Yeah. All right, so 1 molecule of a gas has the mass of this. Determine the thermodynamic temperature of that. So we know that pressure times volume is going to be nkt. And in that case, we can be able to use the concept of pressure times volume is equals to 3/2 Boltzmann constant. Pressure times volume is equals to 3/2 kT. So using this, because we were given the pressure here, yeah, and we have the root mean speed is well seated here, and nkt, but you can see n and n can be able to cancel out, right? So meaning if you take a third times the mass that was given, this mass that was given, times the speed that was provided. The speed that we got here was 502, which is actually 500. So meaning if you are using 500 down here, you're still gonna get it correct. Yeah. So you can be able to square that speed is equals to 3/2 times Boltzmann constant, then times the temperature. So if we are going to make T the subject, you are going to get it as 290 Kelvin. Calculate the internal energy. Internal energy of the gas is going to be 3/2 RT, but internal energy is equivalent to the kinetic energy of gas. Since no intermolecular forces, so it's not going to exert any other force. So we are going to say 6 times 3/2 times 8.31 times the temperature, which is 287. Shall get your value there. 2 metal cuboids P and Q are in thermal contact. State what's meant by thermal equilibrium. We have already mentioned that that is the situation whereby there is no net heat flow between the two sub-objects, and that's when they have same temperature. And don't forget to mention no net transfer. Don't forget to that. Or the net transfer, net transfer is 0. We are also having the concept here that we are working out. We're told that the data P and Q is given here for the two. Specific capacity for P is 390, for Q is 19. P and Q are initially both the same temperature, supplied with this amount of heat. Determine the change in temperature in Q. P is applied, so it means the amount of heat that the other one is gonna get will be the same. So since this is going to be 24 times 10 raised to power 3 from this point here, we are going to say that this is going to be the same amount of heat that's going to be absorbed by the other object. They are going to share the amount, they are going to have the same amount, the amount that is applied, the same amount the other one we're going to absorb. So if we are talking about change in Q, let's look at the specific heat capacity of Q. Is this, and the mass is this. So you're going to say 0.54 specific capacity for this going to be 290 times 0.54 times temperature change plus 0.37 times 910, which is going also to be multiplied by the temperature change. So because this amount of heat that is applied is going to raise the temperature of these two objects, which are, well, both of them are in thermal contact, which means if you work it out, you're going to get 43.9. 43.9. Nitrogen may be assumed to be an ideal gas. The temperature of nitrogen was increased from 0 to 210. Determine the work done on the gas. So the first thing that we're going to do is to identify at 210, what's the volume there? The volume there is 0.38. From 0, the temperature, what's the change in volume in this given point here? We are going to have 0.18. If you subtract, we are going to have that. Work done is pressure times change in volume. So that's why we are going to have work done, change in volume times the pressure. And if you work it out, you are going to get your answer being negative. Work done on the gas. Because the gas is expanding, it means it's going to do work to the surrounding. If they are asking you the work done on the gas, then it means that our answer has to be negative value. Because the gas did work that was done on the gas is negative. But the work done by the gas is positive. Determine the number of molecules. So we can be able to use the concept of PV is equals to NKT. And that is going to be, we know the temperature. We know the Boltzmann constant. Change in temperature here, ready to work it out, but it has to be in Kelvin. Of course, here you are given temperature in degrees Celsius, so you have to be very keen on that. So that's going to be 273. And we are referring to at this particular point. That's where we have the volume, which is 0.18. And then we have the pressure at that given point is 1 point. The pressure is 1.6 times 10 to the power 5. And then temperature here is 0. So 0 degrees Celsius is equals to 273.15 Kelvin. And so that's what you are supposed to do here in order to get 22,400. But what you need to remember whenever you are doing this question is that when a gas expands, it does work. then when a gas does work, the work done on the gas will be negative. But if a gas is compressed, work will be done on it. The work that the gas will do when it's being compressed will be negative, but work done on the gas is positive. Yeah, so the next question was about the root mean square speed, of which you're supposed to use this particular formula in order to work it out. Yeah, so that's gonna get that. We have defined the term specific capacity, so we are not going to repeat on that. We're not going to repeat on that. We have these two graphs. We were told this was losing heat, this was gaining, and they attained a constant temperature or common temperature of 40. So we are supposed to give qualitatively the observations and the conclusion that we can be able to draw this. This is going to lose heat. Which amount of heat is going to be lost? This one is going to gain heat. Which amount of heat that's going to gain? And also you can comment on the common temperature attained, and then you comment on the specific capacity of this and this. So this one is going to have a larger specific capacity. That's why you can see there's a small temperature change in it with the same range. So we're going to say initial temperature of X is 85, initial temperature of Y is that, and they reach both final temperature of 40 degrees Celsius. And the specific capacity of Y is larger than that of X because it undergoes a smaller change in temperature with the same amount of thermal energy. Yeah, so we also have a question here that we are supposed to determine the specific capacity of the metal block X, but we are told the ratio of mass of Y mass of X is that. So we are supposed to do the calculation. So mine was to say let the mass of Y be 1.3 m, then the mass of X will be what? Will be m. So once you've identified that, and then you apply heat lost is equal to heat gained, but the masses you'll use that and their specific capacity were provided, then you can be able to find the specific capacity of the other particular metal. Yeah, so that's the much we can go for today. Guys, if you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to do more tutorials, you'll be notified.